The number of homomorphism of Z onto Z is. We need to find number of onto homomorphism. That is, if F is a homomorphism from Z to Z, then we have to find number of onto homomorphism. Onto homomorphism, it is clearly understood by the word onto. We are interested to find homomorphism from this to this point. We know that Z is generated by two elements 1 and minus 1. Homomorphism, normally we understand that homomorphism preserve algebraic structure, means either plus multiplication, or if any other algebraic structure, then homomorphism preserve. It means that elements of the domain, if follow some rule, then its image also follow some rules. So onto homomorphism, number of onto homomorphism will exist if they generate these two elements generate image. It means only two onto homomorphism exist because of image set codomain has two generators 1 and minus 1. It means that they have pre-images in this and generated by generate entire domain. So there is only two homomorphism. So option C is correct. Let G dot be a group and H be a subset of G, then H is a subgroup of G. If AB are two elements of H, implies AB belongs H. For all A belongs H, A inverse also belongs to H. AB belongs to H implies AB inverse belongs to H, and in option D, AB involve AB in H, then B inverse A inverse in H. After seeing options, you can directly tick the answer C. But other options, why fail? You should know these one. Because if we are picking any two elements, then all four properties will be satisfied for for a group: closure, associative, identity, and inverse. If a star or any other operation is given, it is binary operation. There is no need to check closure property, because saying that binary operation, we say a binary operation whenever it satisfies closure property, otherwise not. If it is simple an operation, then we need to check closure property, otherwise there is no need to check. But here dot is a operation, and normally because J dot is a group, so it is binary operation and it will satisfy for properties. Now H is a subset of G, and we check or say H will be a subgroup of G when H has same operation induced on H, induced on G. So for option A, if we are picking two elements from H, implies that AB belongs H. It is only closure property satisfied here, but not inverse and identity element we cannot satisfy using this condition. So option A is not necessary part. For option B, if for all, if A in H, then A inverse belongs H. Means for each element have inverse in H. So we can say H is a subgroup? No, because of we can't prove closure property. Closure property because of elements are coming from G. It doesn't mean they will satisfy closure property. Yes, they will satisfy closure property, but it may be identity they cannot prove using only this condition. Option C is correct, and we know that option C is one step test for subgroup. Now where is option D is fail? If AB R in H, then B inverse A inverse also H. It means that this property is saying elements have closure property. Elements satisfying closure property, but particularly we say closure property for all elements, but they are combining only inverse element. Suppose A inverse B, and this is element another element C. Suppose this is H. If we are picking an element A and B, then B inverse A inverse in H. But if we are taking A and C, then according to this condition, C inverse A inverse in H, but C inverse is not present in this set. So closure property partially satisfied here, but not for all elements. So only correct option is C. Which of the following statements is true? In option A, in every cyclic group, each element is a generator. This statement is false. You can consider a cyclic group Z. This is cyclic group generated by 1 and minus 1. So not all elements are its generator, because of given is in every cyclic group, each element is a generator. So this statement is false. In option B, 1 and 3 are generators of the cyclic group Z4. Generators generator of Zn are which are coprime with n and less than n. So 1 GCD of 1 4 is 1, and GCD of 4 3 is again 1. So 1 and 3 are generator, and total number of generator in Zn is equal to phi n. Euler-Totin function, you can find number of generator in Zn. So statement B is true. Every set of numbers that is a group under addition, so you can consider R plus is a group under addition, is also a group under multiplication. Every set of number that is group under multiplication is also a group under multiplication. Not R dot is not a group because of inverse of 0 doesn't exist. Every subset of every group is a subgroup under the induced operation. Again, you can consider R plus. This is a group, but n plus is not a group because of inverse elements of natural numbers doesn't exist in set of natural number. So again, this statement is false. So correct option is B. The number of elements in the cyclic group Z42 generated by 30. This question can be solved easily with this formula. Order of a raised to the power r is equal to n upon GCD of n with r. Generated by 30, we know a theorem. Subgroup of cyclic group is cyclic. Also generated by 30, saying that subgroup is cyclic. So generated by 30, it means then 1 star 30, 2 star 30 star is the operation on Z42. Normally operation induced on this is addition modulo 42. So this star normally addition modulo 42, 3 into 30 and so on. So you can find elements of the subgroup. So it may be 6, 12, 18, 24, 30 and so on. Normally how many elements, because of this is cyclic, so cyclic group of finite order, so elements in this set will be finite. By the Lagrange theorem, we know that order of the subgroup divide the order of the group. Group has 42 order, so factors of 42 are 2, 3, so write comma 2, comma 3, comma 6, comma 7. comma 14, and comma 21. So possible order of subgroup may be this or one of them. And we know that consequence of Langren's theorem is that order of subgroup, if it is cyclic and generated by A, element A, then order of this is same as order of element. So order of subgroup is generated by 30. So in place of R, put 30. So N is 42. GCD of 42 comma 30, and GCD of 42 comma 30 is 6. So 42 divided by 6, answer is 7. So which one option is giving 7? Option C is our right choice. So keep remember how to find this order, or in this type of problems always keep remember this formula, apply this formula directly and find the answer. If A is an element of the group G such that order of A is n and n is equal to 2m, then which one of the following is also of order n? We have to find which element as given have same order as A. We know a theorem: if order of A and order of an element suppose B are same, or A raised to the power m, if both order are same, then GCD of order A with m must be 1. If these elements have same order as A, then this condition should be fulfilled. So we are testing one by one. GCD of A is 2m, order of A is 2m, and A square means 2. This is not equal to 1, so option A discard. GCD of 2m with m is not equal to 1 because m is common factor, so option B discard here. Similarly, GCD of 2m with 4 is not equal to 1 because 2 is common factor, so option C is also discard here. GCD of 2m with 3 may be equal to 1 if m is not a multiple of 3. Like if m is equal to 3, then this 2m is 6, then 6 GCD of 6 with 3 is not equal to 1. So in that case, this condition is not fulfilled here, but other option is discard here, so correct answer is option D. Also, because this is a finite group and a finite group has a fixed element order, so m is not varying for element A, so this condition is true and remain hold, so option D is correct.